All right, so this is our last chapter that we're going to be focusing on this semester, this summer semester. And this is where we kind of change gears. So the entire semester we've been looking at functions and their derivatives, first derivatives, second derivatives, and how do we use them to graph functions or to understand what's happening within a optimization problem or something like that. Today, we're going to transition into integrals. So the idea behind this is we know that if you have a function, f of x, so I'm just going to circle f of x here, and we know that if we take the derivative of this function, so we just follow this little arrow down, the little flow chart, we get slopes of the tangent line, okay? Today the question is going to be, if you have a function, let's call it f of x, get out a different color here, and we integrate this function, okay? And that's what this symbol right here means. So this symbol right here means to integrate. The question becomes, well, what does that mean? All right? What do you get from that? And a really easy example for us to look at is going to be the first example, which is going to be areas under a curve. So, area under the curve. Now, like I said, we're going to start off with a really, really easy example here because this is not about the math involved. I mean, I hope you've realized that you're starting to transition into an analytical thinker and not just a computational thinker. A lot of algebra and basic math is all about getting the right answer. What does x equal? However, now we're trying to describe situations. Okay, I know like the one homework problem had somebody row a boat to a certain point and then get off of the boat and walk to a restaurant. All right, it's a very simple example. You row a boat to the shoreline and then you walk to a restaurant. But the idea behind it is, okay, well, what's the minimum amount of time that takes? So the grand concept about that is going to be minimizing time. So I don't care if you are rowing a boat and then walking to a restaurant, or if you're creating a product on a conveyor line, or if you are trying to figure out what is the optimal surface area of a brake pad on car brakes to minimize the stopping time. The idea behind it is you're minimizing something. And to minimize, hopefully by now we know you have a function, you take the derivative, you set it equal to 0, you find the critical values, and that will help you to figure out the situation at hand. With the area under the curve, this is another application problem. So let's take this into consideration here. Pretend that we are driving a car at a rate of, we'll say 60 miles per hour, okay? We drive for 2 hours. What is the displacement? Very, very simple problem here. In fact, you can do this in your head. We know distance or displacement equals rate multiplied by time. All right. So for us, displacement is going to equal the rate, 60 miles per hour, multiplied by 2 hours. Notice the hours reduce. So you are left over with 120 miles, which is exactly what you would think of. However, let's geometrically look at this, meaning let's graph this. All right, so on the x-axis, we have time, which is our independent variable. And that's going to be measured in hours. On the vertical axis, we have velocity, or rate, which is a velocity. Okay, and that's measured in miles per hour. So I'll just put mph. And we know that we've been traveling for 2 hours. So 0.5, 1, 1.5, 2 hours. And I told you that for 2 hours, we were traveling at 60 miles per hour. Okay? So let me erase that real quick. Right here is an example of what happened in our situation here. We traveled for 2 hours at a constant velocity of 60 miles per hour. Now, let me zoom out here a little bit. Up above, we found displacement equals rate times time, so we were expecting 120 miles that we've traveled. But if I were to draw this line right here to connect this, notice the shape that I've just created. The shape that I've just created is a rectangle. And we know that the area of a rectangle is going to equal length times width, or in this case, I'm just going to put length times height. And I'm going to be very specific with this. My length is going to be the measurement of time, okay? My height is going to be velocity. So what we just found here is our time was 2 hours, our velocity was 60 minutes, and we came up with, excluding the units, of course, area equals 120. This area represents the displacement within our situation here. And that's what integration allows us to do. Integration is all about finding the area under the curve. So I'm going to write that right here. Integration is calculating the area under the curve. Now, some will argue that Leibniz and Newton were really big into this, and I'm not going to push back on that argument. I mean, there's a lot of evidence to support that. But there's also evidence to support that Archimedes was actually doing this way before those two mathematicians. So if you want to, you can go ahead and look that up on your own time, all right? But it's really interesting to see just the story behind it. And if you're really interested and you can't find anything, or you just want to ask me, send me an email. I'll point you in I will point you into the right direction so you can kind of do a little bit of investigative research on your own. Okay, it's really good summer reading if you're a math nerd like myself. Now, this was a very easy problem that we looked at. And what made this really easy is the fact that we were traveling at a constant velocity, 60 miles per hour, okay? And that was like the best case scenario. We hit cruise control. There was no wind. There's no hills, no valleys, nothing like that. It was just a straight, and the car was perfect. Everything about this situation was perfect. The question becomes, let's say that we are in the same car again, and let's say we traveled for 2 hours again. However, throughout this trip, there were some hills, and so we went uphill, we went downhill, and we wanted to find our displacement here in this situation. Now notice my velocity as we were going on the trip, and I'm kind of just doing like dotted lines above it. All right, my velocity changed between 0 and a half hour. Our velocity was increasing. Then from 0.5 to 1, our velocity went down. And then from 1 to 1.5 hours, we kind of leveled off and we started to increase again. And then 2, it looked up to 2 hours, it looks like we were increasing again. The question becomes, what's my displacement? Now, you and I both know displacement equals rate multiplied by time. However, my rate was not constant. It was constantly changing. So how do we go about a problem like this? Okay. So what I've done is I have an example here. It's a really easy looking example. Okay. And this is the function x to the second power. Okay. And notice what I have underneath here, underneath this curve, is a rectangle. Now, the reason why I have a rectangle is because I know the area of a rectangle. In other words, and this is a lot of mathematics, and to be honest with you, this is life, okay? You are going to navigate your way through this thing called life, and you are going to encounter problems that you have never, ever seen before, all right? It is up to you to try to figure out the best possible solution. And sometimes you find a solution, and it's not the best, but at least it's a solution, and then you can work with that, okay? I'm sure you're going to hear this from other professors. I am willing to work with somebody who is willing to help themselves. That is my goal, is to help people help themselves, all right? So here's a problem, and the problem is find the area underneath the curve of f of x equals x squared. Now, we do not have a formula for that. There's no formula that gives you this, okay? So what I do is I lean back on my my previous knowledge. So I'm gonna go back to our notes real quick, because I'm just gonna do this. All right. Call this A. We'll call this B. My goal is to find the area of this underneath this curve. Okay. Now, like I said, this is constantly changing. The slope at this point right here is completely different from the slope at that point right there. They are different. Okay. Now, so what am I going to do? Well, I'm going to lean back on what I know. I know the area of a rectangle, and that's very easy. So if I were to take this, I could draw a very rigid rectangle right here, and I'm going to shade it in. But notice, if I wanted to find the area of this rectangle, area would equal the change, or this distance right here between A and B. So I'll call it the change from A to B multiplied by the height of my rectangle, which is right here. So that's going to be f of b, okay? But when I do this, we're going to get a very large overestimation, okay? And the reason is because we have all this area above the curve that I don't want, okay? But the idea is there. Instead of just doing one rectangle, okay? Now, you're going to have to excuse me here because I'm going to have to erase some stuff. So instead of doing one rectangle, what if I decided to break it up a little bit? In other words, right down the middle here, I create another rectangle. Okay, so give me 1 second here. I'm just gonna clean this up. You'll see where I'm going with this. So now, if you look at this rectangle here and this rectangle here, notice I still get the area under the curve, which is what I want. Okay, this is the area under the curve of what I want. Unfortunately, I still get this over approximation, which is right here. However, it's not as large. That over approximation is not as large. So I'm still getting an overestimation, except it's not as large as what it was previously. Okay? Now, I'm very specific with how I'm drawing my rectangles right here. These rectangles that I'm drawing are called right end rectangles, okay? And the reason why they're called right end, okay, is right here, the tip of my rectangle on the right side is actually hitting the function. So this is going to give me an over approximation. Now, if we were smart about this, I'm just doing the same thing, okay? We can actually do what we call left end rectangles, okay? So let me show you what that looks like. So right here, I'm going to cut this in half again. But in this case, watch this. There's my first rectangle. It's just a line, and it follows the horizontal axis. But notice that the left end of the rectangle touches my function at point A. Now I'm going to draw another rectangle, and I'm going to make sure that the left side of it touches my function again, okay? And then this is it. I'm only going to stop because I only want two. But notice here, I get the area of two rectangles. However, in this turquoise here, I am missing this area right here. So this is what we call an underestimation, okay? Now, on the board, you have two situations. Right-ended rectangles gives you an overestimation. Left-ended rectangles gives you an underestimation. So area of the right and area of the left. And here's what we know. We know that the true area, and I'm going to write this in black. The true area has to lie somewhere in between my overestimations and my underestimations. So if you're sitting there thinking about it, hopefully your mind already went to, well, why don't we just draw more rectangles? And that's the idea behind integration. So we're going to go back to my picture here. So notice, excuse me, notice here, this is the left-ended rectangles right here. So let me scroll down here a little bit because I'm going to read to you on the left-hand side. So my choice of method, if C equals 0, then we're going to have left-handed sums. If C equals 1, we will have right-ended sums. And then C equals 0.5 for midpoint sums. I'll get to the midpoint in a second. What we're going to do is we're going to focus on just left hand and right hand. So right now, if you're looking on the left-hand side, C equals 0, which means I have left-handed sums. Okay, and notice that right there is my first rectangle from 0 to 4. And then my second rectangle is going to go from 4 to 8. So I only have two of them, okay? Now, my interval here is from 0 to 8. What I want to do is find the area under the curve from 0 to 8, okay? Now, right here, I equals 64. That is the sum. In other words, if we were to take the area of this rectangle right here, all right, hopefully you can see that in the middle of your screen towards the bottom, okay? If we were to take the area of that, it would be the distance from 0 to 4, which is 4, times the height of the function, which is 0, because 0 to the second power is 0. So we would get 0 here. However, if we were to look at this situation right here, okay, from 4 to 8, the distance in between 4 and 8 is 4 total units, okay? But then the height of this rectangle is going to be f of 4. So this is going to be 4 times 4 to the second power. So let me go back to our math real quick. So 4 times 4 to the second power equals 4 to the third power, which is 64. All right. Now I'm going to go back to our picture. So notice here I have I equals 64, which is the approximate area under the curve. But we know that this is an under approximation. Okay. So now what I'm going to do is I'm going to change this to right-ended sums or right-handed rectangles. And notice just like in the theory part of this lecture, we have this over approximation from 0 to 4 and then another over approximation from 4 to 8. And notice that the integral approximation for this is 320. So the true area in between these two curves has to be in between 64 and 320. Now, you can get a pretty good idea of this if you were to take 320 and just subtract 64. So 320 minus 64 right now is 256. So we should be thinking, maybe the area is somewhere around 256, okay? However, we only have 2 rectangles. Let's see what happens when I increase the number of rectangles from 2 to 4. Now, if you're thinking about this, and what I want you to do is I really want you to think about this. So if you can, after I ask this question, just pause the video and think, and then try to come up with this answer. If I increase the number of rectangles, what's going to happen to my interval? Is it going to get larger, or is it going to get smaller? Okay, so if you pause the video, think about it, and then whenever you got your answer, unpause. I'm just going to keep moving on because that's what I can do in a video. So I'm going to go ahead now and increase the number of rectangles n equals 2 to n equals 4. Okay? So, and we're going to do the same exact thing that we just did previously. So we're going to start with the under approximation first, okay, which are going to be the left-ended rectangles. So notice that I have 4 of them. It's kind of hard to see here, so I'm going to zoom in. Let me just zoom in a little bit. There we go. So at the bottom middle of your screen, from 0 to 2, there's your first rectangle. From 2 to 4 is your second rectangle. From 4 to 6 is your third rectangle. And then from 6 to 8 is your fourth rectangle. I'm going to find the area of each one of these, okay? And I'm going to do it by hand in a second. Right now, this is all about just visualizing and trying to interpret what's happening, okay? So my underestimation of the area for the area underneath this curve from 0 to 8 is 112. So let me write that down. Now we're going to do the right-ended rectangles. Now this is my over approximation, which is 240. And if you guessed that your interval would actually get smaller, it would decrease, then you were correct. So we went from 64 to 320 for our first interval with 2 rectangles. So n equals 2. To a new interval, which is much smaller, 112 to 240. So now, if we were to subtract those two numbers, okay, if we were to subtract these two numbers, we get an area of 240 minus 112, which is now 128. Okay? Now, notice your interval is getting smaller, which means the area itself is also going to get smaller because what you're doing is you're starting to actually zoom in on what the true area under the curve is. Now, what I'm going to do is I'm going to just let this slider go, and you're going to see what happens to the area, or to all these little rectangles underneath this curve. So we'll start off with the left-handed rectangles first. And notice that as I increase the number of rectangles, notice I'm still getting an under approximation for all these rectangles underneath the curve. Right now I have 49 of them, 49 rectangles underneath this curve, okay? Let me zoom out a little bit. There we go. But notice that the amount of the underestimation is not as great as if you only had 2 rectangles, okay? Now we're going to go back. We're going to go back to 4. And I'm going to go ahead and look at, okay, well, right-handed rectangles. Now, we know we get an over approximation here, all right? But notice that the amount of over approximation that I get is decreasing. It's getting smaller and smaller and smaller. So, what was it, 49 last time? Yeah, so 48 is fine. So, notice that, you know, the amount that you're over the curve is not as much. Now, I want us to focus on this number right here. With an over approximation, it's approximately 176. With an under approximation, it's 165. And we are estimating the area under the curve, all right? So once again, underneath is 165. The over approximation, I forget it already, so I need to go back, is 176. And this is with n is approximately 49 rectangles. And if I were to subtract these two numbers right here, now you're getting 11, okay? So we're trying to actually figure out what is what is this area under the curve, okay? We went from 256 to 128 to 11, and notice that as this number goes to 0, these two numbers, your endpoints, are actually going to start to become the same exact value. And that's what's happening here. The more rectangles we have, the closer we're zooming in on this true area underneath the curve. Now, mathematicians have been doing this for a long time, okay? And then one person came along and actually really, really broke this down and made it really simple, okay? So what we're doing here is we're finding Riemann sums, okay? So approximate, let me zoom back in here. So by, excuse me, by drawing more and more rectangles, we're finding areas under the curve. We're approximating areas by using Riemann sums. Now, there are different types of Riemann sums. Notice, and I will go over the definition here in a second, but what I want to focus on is towards the end. Notice we have left Riemann sums, we have right Riemann sums, and then we have the third, which I said I'd come back to, which are midpoint Riemann sums. So let me show you what the midpoint Riemann sum looks like. So if I come back here to our example, I'm going to decrease the number of rectangles again. So we'll call them 2. Come on, work with me here. Here we go. Okay. Perfect. So with left-handed sums, we found the area under the curve estimated to be 64. And with right-ended, we found that it was 320. So there's a big difference. What if we went in the middle? In other words, what if we allowed the middle of our rectangle to actually hit the function? Well, notice that if I allow the middle of my rectangle to hit my function, then I get 160 for a total area. And as n increases, so I'm just going to let this play, watch the area, the approximation, I. Watch what happens here. So there's 59 midpoint rectangles, and the area under the curve is approximately 170.5, or I'm sorry, 171. We'll round it to the nearest whole number, okay? So it's approximately 171, all right? What I'm going to do is I'm going to teach you how to actually calculate the true area underneath this curve, okay? But first, we have to understand how this is working, okay? So I have an example for us. And before we can do the example, we're going to read this definition of a Riemann sum. So suppose f is defined on a closed interval from a to b, which is divided into n subintervals of equal length. And we're going to call those n subintervals of equal length, we're going to call them delta x. In other words, the change in x. If x sub k star is any point on the kth subinterval, for k from 1 to all the way to n, then you have this formula right here. So real quick, let me go over this. So this right here, I'm going to come all the way to the end because this is just the general form. Remember, we are trying to find the area under the curve. For chapter 5, even into Calc 2 and Calc 3, you're finding areas under the curve, which is integration. Okay, Calc 3, you do a lot of derivatives again and stuff like that. In fact, Calc 1 and Calc 3 are essentially the same course, just Calc 3 is in 3 dimensions, where Calc 2 or Calc 1, we only talk about x and y. But anyways, more on that later. So our goal is to find the area under the curve. We're using rectangles to do that. And we know that the area of a rectangle equals the length times the height, okay? Or a side times a side, okay? So when we talk about a Riemann sum and we have these subintervals of equal length, okay? And we look at this function, well, the height of the function is going to be the height in this formula for the rectangle. The delta x is our length. So notice that what this is telling you to do, what this formula here is telling you to do, now what I'm going to do is, let me just connect these, and then I'm going to highlight the formula. What this is basically telling you to do is find the area for each individual rectangle. So this is going to be, rectangle 1, rectangle 2, all the way up to the nth rectangle, however many you have. Find the area of each individual rectangle and just add them all up. And that is called a Riemann sum for f on the closed interval from a to b. Okay? So what I'd like to do is show you an example of how this works, okay? So here's our example right here of approximating areas using Riemann sum. So let me zoom in here a little bit. And there's two parts, A and B. I have the graphs. This is the graph for A, and this is the graph for B, okay? Probably going to have to move B down a little bit because I'm going to write a lot here. So let's read the problem first. The velocity of an object moving along a line is given by v equals vt squared plus 3 feet per second on a closed interval from 0 to 4. Part A says, divide the interval from 0 to 4 into subintervals from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. So we have 4 total rectangles. So I'm just going to label this R1, R2, R3, and R4. And on each subinterval, assume that the object moves at a constant velocity equal to the value of v evaluated at the midpoint of the subinterval, and use these approximations to estimate the displacement of the object on 0 to 4. So then it says C part A of the figure. So this is part A of the figure right here. Okay? So, get out my black marker here. Give me 1 second. Here we go. So the displacement of the object is equal to rate times time, which that formula should look very familiar now. That's nothing more than the area of a rectangle, okay? On each subinterval, what we're going to do is approximate the velocity by a constant equal to the value of v evaluated at the midpoint, okay? So our first subinterval is going to be 0 plus 1 divided by 2, which equals 0.5. Now, what I just did is what we call a rectangular partition. So give me 1 second. I'm going to change my color of my pen here. So this is called a rectangular partition. All right? And what a rectangular partition actually tells us is, suppose you have a closed interval from A to B containing n subintervals. So however many we want, okay? We can call these intervals x1 or x0 to x1, then x1 to x2, all the way up to xn minus 1 to xn. Okay? And these are all equal length. The change in x, in other words, delta x, is going to equal b minus a divided by n, with a equal to the initial point of that interval, b is equal to the final point of that interval, okay? And n represents the number of intervals that you want. So if you want 8 intervals, then n would equal 8, okay? So what this is going to do for us is this formula, which is really basic to understand, this formula just helps me to determine where are these midpoints at, okay? So the first midpoint is 0.5, which I think you could have figured that out on your own. However, this is a very specific process here. Okay? All right, so back to the problem at hand. We could do this for all the other midpoints as well. So for rectangle 2, the midpoint is going to be 2 minus 1 divided by 2. Sorry, made a mistake. It's 2 plus 1 divided by 2. Sorry about that. But this is going to be 3 over 2 or 1.5. So this is going to be 1.5. And then you could do the rest, but we get 2.5 and 3.5 respectively. Okay, so the next thing we're going to have to do is find the height of each one of these rectangles that we drew, because the height is going to represent the velocity. So we need the velocity at 0.5. We need the velocity at 1.5, velocity of 2.5, and lastly, the velocity at 3.5. And the reason why we need that is because displacement of the object is going to equal the rate times the time, which we know the rate is going to be the height and time is going to be the length of each one of these rectangles. So V of 0.5. Now, recall that the formula was 4t squared plus 3. So when t equals 0.5, V of 0.5 equals 4. Let's come over here to the right. And by substituting in for all the different values here, V of 1.5 equals 12. V of 2.5 equals 28. And then V of 3.5 equals 52. Okay? Now, if we want to find the approximation for displacement over the entire interval, so to find the approximation for the displacement over the entire interval, what we're going to have to do is find the area of each one of these rectangles, okay? So our displacement is going to equal rectangle 1 plus rectangle 2 plus rectangle 3 plus rectangle 4. So remember, area is going to be the rate times the time. Now, what that means is V of 0.5 times delta x, our change in x for the first rectangle, plus V of 1.5 multiplied by delta x for the second rectangle, plus the velocity for the third rectangle times delta x, and then the last one. Now, what's nice is we already went ahead and we figured all this stuff out. We know, and I'm going to go back up to our picture. We know the length of this entire rectangle is from 0 to 1. So delta x is going to equal 1 second. Now, if you look at this formula right here, this delta x, notice that if I just do it for the entire interval from 0 to 4, I will get 4 minus 0 divided by 4 rectangles, which is 4 over 4 equals 1. So what I'm going to have to do here is take V of 0.5, which is 4 times 1, plus V of 1.5, if I just scroll up again, remember that was a 12. So this is going to be 12 times 1, plus V of 2.5 is 28 times 1 plus V of 3.5 is 52 times 1. And when you add all these up, you get your displacement to be 96 feet. So just to recap, the velocity of the object moving along the line, V equals 4t squared plus 3 from 0 to 4. The displacement is 96 feet. Okay? Now, the only different part for part B, and I'm going to rewrite part B as just repeat part A for n equals 8 subintervals. So all we're doing here is just making more rectangles. So our displacement for this is just going to equal rectangle 1 plus rectangle 2 all the way up to and including rectangle 8. So you're going to have to do this problem the same exact way. It's just all over again. So what I'm going to do is I will find the first interval. So here's rectangle 1. And we need to find that midpoint right there. Well, we know for this subinterval here, it's going to be 1 minus 0 divided by 8. Okay, because now, oh, sorry, wrong one, divided by 2. And I'm wrong all around. There we go. Now I got things labeled. So this midpoint right there is going to be the midpoint of 0 plus 0.5 divided by 2, which is 0.25. So that's our midpoint, 0.25, okay? Now to find all the other midpoints, I gotta be honest with you, it's sometimes it's just a lot easier just to, once you find the first, okay, excuse me, it's just, you create a table and just figure all the other ones out. So what I'm gonna do here is just write subinterval. Looks like a V. There we go. And the midpoint, okay? So the first interval is 0 to 0.5. And we found that the midpoint was 0.25. Now the second is going to be 0.5 to 1. And that's going to be 0.75. Your third interval is 1 to 1.5. And this is going to be 1.25. Your fourth interval is 1.5 to 2. And that's going to be 1.75. And you should start to hopefully see a pattern developing here. The distance from 0.25 to 0.75 is 0.5. The distance from 0.75 to 1.25 is 0.5 again, and so forth. So for the next interval, if you just take 1.75 and add 0.5 to it, you're going to get 2.25. And you just keep doing that from now until you get to the final interval. So, oh, sorry, that's supposed to be a bracket. So now we got 2.5 to 3. And that's going to be 2.75. And then 3 to 3.5. My midpoint is 3.25. $3.5 to 4 is 3.75. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8 intervals. Good. We have all the midpoints. And if we looked at just delta x of the entire interval, we're going to get 4 minus 0 divided by 8, which is 4 over 8, which is 0.5, which is what it should be, because we are moving 0.5 units to the right every time we create a new rectangle. All right. So now you got to find the heights, and I'm going to zoom in for us here. You got to find the heights of each one of these midpoint rectangles, because that is where it hits the function. So for the first rectangle, the height is going to be v of 0.25. Now, we know, now let me zoom out here a little bit, because, oh no, I'm smarter than the average bear. I'll just use a smaller pen. So v of 0.25 is going to equal 4 times 0.25 raised to the second power plus 3, or v of 0.25 is equal to 3.25. So that's going to be the height of this very first rectangle, 3.25. And you do that for your second rectangle, your third rectangle, your fourth rectangle, and you keep doing that all the way up to your eighth rectangle. So what I'm going to do here is just create a table and just fill in the table for us. All right, so I promised you a table. So what I did is I paused the video real fast and I did it in Excel. This is much easier. And here's our table right here. So let's see, let's make it a picture. That way I can do this. Perfect. All right, so here are my intervals, my midpoints, and my velocity at each one of those midpoints. Okay. Now, displacement. Use a different marker here. Is going to equal all of my rectangles added up. Okay. So what we're going to have to do is do every single rectangle and find v of 0.25 and multiply it by 0.5, which is our delta x, and then v of 0.75 times delta x again, which is 0.5, and we do this all the way up to v of 3.75 times 0.5, which is our delta x again. Now, there is an easy way to do this without having to just multiply every single little thing. Notice that, and I'm gonna use a highlighter real quick. Notice that every single one of these terms has a 0.5 in common. That's the delta x. Okay? So if I were just to take 0.5 and just factor it out, then all I have to do is just add up all the velocities all the way up to and including the very last velocity. Just add them all up and just multiply all that by 0.5. So that's what I'm going to do here. So just give me a second. Let me catch up. So we got 0.5 times. Now I'm going to take every single one of these values from my table and just add them up. So I'm just writing everything out so you can see everything. Yeah, the last one's 59.25. So I'm just going to add them all up and then multiply it by 0.5. So we get 194 times 0.5, which our displacement is going to be 97 feet. Now, every single one of these problems in your homework, and there's not a bunch, I think there's like 5 or 6 questions. Every single one of the problems is done the same exact way, which is figure out what your intervals are, if you want left or right-handed sums or midpoints, and then just follow the Riemann sum formula. So if you notice, with 4 rectangles, we get 96 feet. With 8 rectangles, we get 97 feet. So we get a better approximation of the displacement of this object moving along a line. And that's going to be it for this video. I know it's a long one, but it's really crucial that we understand what's happening when we find areas under the curve. In section 1, there's this part of this section that deals with Riemann notation and summation notation. We're not going to worry about that. All we're going to do is just focus on just creating rectangles underneath, and then figuring out from there how to find or how to approximate areas under the curve. In the next video, that deals with definite integrals. That's where I'm going to teach you actually how to find the true area underneath a curve. So I'll see you in the next one.